Hi everyone. So my talk is going to be a little bit of a different style to Eddie's, for those who just saw that. Eddie was talking very much around some kind of things that are quite close to production, quite like stable things. My talk is more around the journey I took over the last few months playing around with neural networks. So I work at List. I've been calling myself a data scientist for, I don't know, 4 years now, probably. I've been playing around with machine learning and things for more like 7, but I first started playing with neural networks very recently. I decided to jump in somewhat at the deep end, so I played with a couple of little classifier networks and then decided to play with metric learning, which is a different beast entirely. So I thought my talk today would be best around discussing the nature of that problem and all the ways in which I did it wrong, I guess. So I hope this will be useful for some of you. So there's a couple of things to consider here. There's two kind of concepts that we need to consider. One is the nature of what I'm trying to find, which is pairs of products. So this is from our site. And what we have is 3 different products here that are three blue pairs of shoes. I think actually the common projects were from the same that we've seen in the last set of slides. But these are all the same product. And yet they appear as different products on our site. And that's not ideal. What we'd like is to collect those 3 things together and show them as one thing. And the size of the problem is relatively large. We have of the order of, we have 100 million images, kind of 106 million images at last count. We have more than 30 million products in an ungrouped form, and we've managed to group them down quite a lot to more like 10 million, but should be dropping that further than that. There's still a lot of duplicate content still remains. We know something about all of our products. We know who the designer is. We know what type of product they are. But if you try and do a brute force search on this, if you take classification, you can take a random sample and ask people to label them, and you get 1,000 labels, and that's great. You get fairly rough spread of your categories. If we pick random pairs where they share a designer and they share a category, only 1 in 1,000 will be a match. So brute force labeling of this is really, really expensive. We brute force label categories. We can't brute force label duplicates. It's just too much money. And it's a useful thing to do. It's great for our users. It's nice to have one product in a feed, to be able to show when searching a single product, and then when you actually get to it, let people know where they can buy it from a lot of different places. It's also very useful in more of a selfish context. So as a data scientist, I'd like to work with cleaner data. So if we can take all of these things and combine them into one entity and say, this is just a lot more data for the same entity, and then we can classify that entity in one go. That's really useful. So it helps with classification. Recommendations is really helpful. When a user visits either of these different products, it's useful to actually say they visited the same product and to combine the information from those. So it's very, very helpful. It's also useful when kind of things like marketing and attribution. You know that you don't have to try and have different competing products that you're putting out there, and you're trying to drive people to your site. You actually put one product out there that's better. So before I talk about this, I actually wanted to talk a little bit about something that I think kind of came up a little bit in the questions before, and that's to do with the kind of perspective of having multiple images for a product. So kind of at the top here, you can see a kind of collection of images that are fairly good images. If you look at any one of these, it's fairly easy to tell if you have a kind of pair of these, whether you're looking at the same product or if they're different products. But if you take these, I'd be quite hard pushed to tell if these are necessarily these two. Are these the same? Are these different? And this is particularly difficult for the nature of the way some designers take photographs. So if you take some red Converse and some blue Converse shoes, what designers will often do is they'll take lots of side shots of the different colors. They'll flip one of them over, take a picture of the sole, and then use that for all the different colors. So if you do exact match, you can get a perfect image match across 9 colors, 12 colors. And it's perfect. It's definitely the same image. So that doesn't really help you very much. So I'm building somewhat on the work or quite a lot on the work that Eddie's been doing, and in particular on the representation work that he's been doing. So I thought, well, let's see if we can take advantage of that and try and address part of this problem. So we want to understand something about getting perspective, but we don't want to have to go through the work to kind of huge amounts of work to do this. We want to do it in the simplest way we can. So the first thing we do is we train a neural network for classification. It's not a super simple task unless somebody's already done it for you, which in my case that is true. But in general, if you want a pre-trained neural network, they're actually fairly easy to get hold of. There's quite a lot of them, them available for fairly general purpose data sets. So getting hold of a pre-trained network isn't too bad. Then you want, so in my case, I wanted to know about, I think you can maybe faintly see, it's the nature of watermarks on laptops and projectors. We've got this idea of a side-on shoe. So wind back a couple. So what I want is to label one image that's a side-on shot, so something that you can fairly easily identify the product from, and one label that is not, something like a sole or kind of an end-on shot of a shoe. So I want one label of each, just as a starting point. If you want to train a model, you need to have at least one label of each class. That's a good place to start. Then I will train a simple model. In this sense, I mean simple in that a support vector machine is going to have a relatively small number of parameters compared to, so in this case, it takes in a 9,000 dimensional representation, so it has 9,000 parameters or of that order, compared to a neural network which has 16 million. So it's a simple model. And having trained this model on 2 labels, you can then ask it which of the remaining samples it finds confusing. So in this example, confusing really means the probability that it's one class or another is about the same. It's kind of equally likely that it's anything, so it doesn't know. So if you label this sample, you are likely to get a label that's useful for describing the partition in your feature space. And then repeat. Repeat this until you're bored. For me, bored was about 500 labels. And then I got some friends to do some more, and we got up to maybe about 1,000 labels. And that was sufficiently boring. And then you can see what you get. So these are some predictions of pose on images that were never seen. Like none of these products were seen. None of the designers of these products were seen by were featured in any of the labels. And so we have one product per row. And the very left-hand image is the most likely to be a side-on image for this product. And then they work back to the least likely. So it's not perfect. But given that it's 500 labels and we have 6 million products, in this particular data set, my data set I'm working with is all sneakers. So this is only about 100,000 products, I think, or 50,000 products we're working with. But even so, it's doing a very nice job of neatly ordering the images. And not only does it a reasonable good job of finding a good first image, but it also gives a fairly kind of consistent progression to the remaining images. Now, if you just took raw images and you tried to do this, I think this would be a fairly difficult task. So there's kind of a question of why this works. So we've seen pictures a little bit like this before. You can see like the islands. This is using t-SNE to take this high-dimensional space and then flatten it down to 2 dimensions, where distance in this 2-dimensional space is similar to distance in the high-dimensional space, as you know. So if we just zoom in on a few areas, one of the things we find about this natural representation here, and this is at a lower level than what if you saw Eddie's talk, then I've thrown away all the fully connected layers, and I'm at the end of all the convolutional, so it's a little bit more low level than that. And we find that pose is actually quite a natural clustering. So it's not a surprise that this space can be used to pull out particular pose features. The other thing that's quite interesting is you find that actually in any given image, the types of shoes that are close together within these regions are of similar types. So you get like athletic sneakers kind of close together. You get like plimsolls close together. Anything with a white sole tends to kind of end up nearby. So there's quite a lot of information in this space. So maybe this representation is useful to look at the duplicates. And this is great, but neural networks are great. Support machines are great, but maybe I should play the neural network because they do win everything. They do seem to be fantastic. So let's build one of those. Now, you've seen the kind of structure we've had before, but I want to talk about, and I imagine a lot of you here are pretty familiar with classification networks. They're very, very common, and I know a little bit about them, but one thing I learned about as part of this is that you can have alternate types of network structure that are quite interesting. So the structure I'm interested in is for metric learning. So you can start with 2 images, and you can start with you can take a network, and then you can pass one of your images through this network and get a representation. You can pass another image through the representation, and pass them both into your loss function. And this is in some way analogous to what we do with the multi-image work, but in this case, we're not going to go and do average pooling. We're going to pass them into a specific kind of loss function designed to deal with this style of network. And then we can backpropagate that one loss through the whole network, and it will adjust the weights of one single network in order to make in order to be useful for what we're trying to do. And in particular, we're going to use contrastive loss. So I use contrastive loss. So this is a loss function that tries to take things that want to be close together, that you say are the same, and bring them close together, and things that are far apart, bring them further apart. So two fairly critical terms. We have one term that activates if the sample is a pair of things. This takes pairs, this style network. So if the pair is labeled as being the same, then your cost is proportional to how far apart they are. If the pair is different, then the cost is proportional to how close they are if they're closer than some distance. But if they're outside of some margin, typical margin is 0.2, so if they're more than 0.2 apart in this space, they don't cost anything. So we're not trying to move things arbitrarily far away, just far enough to have a bit of space around things. And then we just combine these two terms and average them, much like things like log loss and those kind of things you'll be familiar with. So how did I actually go about the process of doing this? Well, I read a paper. It's a good paper. I implemented the network. And I sat and watched the loss decrease. I don't know how many, everyone who's actually done this, when you actually start printing out the loss as you work through, it's strangely satisfying. You can occupy quite a lot of minutes of your day just watching the numbers go down. And then you look at the results, and we find out whether it actually worked. And it kind of didn't. It kind of didn't work very well. I got these first results. And when I first looked at them, I thought, oh, that's quite nice. That's quite exciting. Maybe that's worked. And then I look a bit closer, and, well, the things that, there's trainers with trainers, but that's because they're all from a designer that only sells trainers. So, of course, they're the same. So you have this problem where you can convince yourself it looks great, but when you actually look at a bit more detail, you go, it's not working that well. But the loss had gone down and the accuracy had gone up, so I was a bit confused why this seemed to have been working. My numerical measures look great, and I'm doing cross-validation, and I've held out test sets, all looking great. But it turns out that the key to where this was going wrong, the clue, was in this line here. These are all just the same images, like it's different shots in the product. And effectively, there was too much noise in our data. So when I went back to our catalog and we looked at individual products, what we found is that because of some quirks of our spiders, when a retailer moves a page for a product, we potentially see the same thing and then we merge them together. So you get the same image multiple times in a product. And so it was just noise, it was just duplicates. And my model was cheating. So it became an important step was to go and clean up the data. I took a step back from the neural networks for a little bit here, and I went to look at something that we'd previously considered for cleaning up the data and cleaning up images, which is p-hash. For those who don't know, this is perceptual hashing. It has a kind of similar analogy to like hashing, cryptographic hashing, except that it has this nice property that images that look the same are very likely to have the same hash, and images that look different are very likely to have a different hash. So it's kind of, it's useful to find things that have been like recompressed or resized, but still you want to kind of step to the same. But it's only designed to have things that look like exactly the same image. So we can find identical images and match them on this basis. But it does have the problem of having unacceptably high false positives and negatives, really far too high. But one thing you can actually do is, because we have a collection of images, you can rely on the fact that multiple images must match. And this is something we hadn't been doing in the past. And I went and applied this to our data set, and it turns out of our 10 million products, there's about 1 million that we can just compress together on the basis of they have enough corroboration between the p-hashes between images to know that they're good. This is great. It means we can get a better data set to do the training on. The other thing is there are cases where there's not enough corroboration to know that whether or not you should combine these things. But all the images that are in that state, all those confusing images, you can just strip out the data set because you've got enough images per product. This isn't too much of a problem. You still get a reasonable set to train with. So I did this. So now I have a nice clean data set, and I went back and I went to my modeler and I trained it, and I got my loss, and this isn't going down. It's a bit upsetting. These take quite a while to like code up and train as well. Like I'm doing this in Chainer, which is a lovely library, but it's not like scikit-learn. Like there's quite a lot you have to do to get this working. So and even just downloading the images takes several days. And, so hey, probably should tweak my hyperparameters. Just throwing them defaults is not that great idea. So this is a valuable thing. You need to go through and just make sure everything's kind of set up sensibly and try exploring the space a bit. And I did this, and I spent a couple of weeks on this, and they're still not going down. It's quite despairing. And I should say, this was like a few weeks ago, and I had this talk. So, OK, I mean, the paper was from 2005, right? Neural networks have moved on since then. So let's read some more recent papers. These two papers are particularly good. they have a different approach, and in particular, they talk about triplet loss rather than pairwise loss. So contrastive loss is I've got a pair. Imagine you're working in 2D space and you have a big 3D space and you're trying to kind of flatten it down to 2D. And what you're saying is I want to pinch these 2 points here. I want to pinch them together because they're the same. And I've got these 2 points and I want to move them apart because they're different. And you can do it any way you like. And because they're unrelated, you can kind of warp the space in some unusual ways, and it doesn't really matter. And as long as if you have really big mini batches when you do this, then this is kind of stable. But if you work with small mini batches, then you can see how this can be a little bit unusual. Whereas the triplet loss is a little bit different. You take one anchor, and you have to have one thing that you know is the same and one thing that's different. And so you distort the space relative to an anchor point. So the principle sounds great. It should be more stable. So we should work with that. And again, we want to go watch the loss decrease. Oh, actually, something I don't say in here is part of working with triplet loss as well. There's a lot of discussion around using curriculum learning, so particularly using what's called soft negative triplets. And that's where you only consider triplets that are difficult but not too difficult. So they've got to have gradients for both the positive and negative cases, but they can't be like completely inverted and really like make it really hard for the network because that creates more instability. So extra complexity. But anyway, so get one of these, code this up, and watch the loss decrease, and then look at the lovely results. So hey, it's still not working, and it's okay. It's okay. I've still got a week and a half to go. Well, we all know the unreasonable effectiveness of data, and I'm still not working on a particularly huge data set here because I'm trying to get this stuff. It's a few thousand by maybe I just need to throw more numbers at it. I mean, to bigger networks. So let's do that. Oh, no, that doesn't work either. Okay, so I'm rather despairing at this point. Yeah, there's probably something I'm doing wrong in my approach here. Maybe there's a better way of approaching how to kind of train these networks. So at this point, I took quite a big step backwards, and I thought, well, maybe the first thing I should check is I can do a really, really simple case and just make sure that actually this is all working. So I took quite a large quantity of code and just like threw it away, and I went and rewrote from scratch. Very, very simple. I want two products. I've got a few images from each, but I want two products, and I want to project them into a two-dimensional space, and one that I can visualize, one I can see what's going on, and just check this makes some kind of sense. Well, hey, I mean, it does something, but it's quite aggressive what it does, but it's kind of going the wrong way. This wasn't really ideal. And I played with the gradient, the learning rates and stuff, but I mean, this happens. This really happens, whatever your learning rate. You can eventually get your learning rate to the point where it kind of doesn't do this for a while, and then it does this anyway. It's really annoying. And I should say, at this point, I've gone back to contrastive loss, because contrastive loss is a lot easier to think about and reason about. So yeah, this wasn't so great. But I thought, well, let's just have a bit of an explore. And it's a sufficiently small problem that I actually started working through the maths of this and looking at it. And I'm doing 9,000 dimensions into 2 dimensions. So it's a single matrix transformation. It's a fairly simple thing to actually debug and kind of work through what's going on. So I went through this. And one of the things I found quite quickly is I can repeat the same process, but I can see the most extreme gradients that I get at each stage. And it's fairly clear that having a gradient of like 50 when your weights are like more like 1, when your values are more like 1, is probably a little problem. So I implemented gradient clipping. This is quite a commonly recommended thing. And it turns out this actually solved that problem. So this was like a kind of really nice breakthrough where suddenly I've got a small problem, a small network, and actually with my 2 samples, I'm able to get to a position where it does actually learn something, and I can see, I can see what's supposed to happen. I can see the loss go down, and it was quite nice to see the numbers go down. But I'd had this before, and it was like I've seen this. I've seen the numbers go down. It doesn't actually tell me it's really working. So I actually decided that, well, I've only got 2 dimensions, and I've only got like 7 images. So why don't I just look at them? So this is when you randomly initialize the network, your images end up somewhere in your 2D space. And one of the things you can do is simply look at where they are, update the network, and look at where they move. So you can watch the network learn and figure out how to move them around. And this is quite nice. And you can see the kind of some of the quirks in neural networks that you don't get like nice kind of simple smooth stuff. You get these kind of they kind of sit around for a while, and they can kind of have big movements. And this is quite consistent. Like I've done quite a lot of this since then. There's a lot of consistency that they don't learn quickly and then slowly, and this kind of nice exponential decay thing isn't quite what happens in the kind of the state space. You also see that at the end, they always end up oscillating. Like they hang around, and that's, unless you start decaying your learning rates, this is what happens. And that's where you tend to get things like overfitting and stuff happening. So that was quite, like, for me, that was really nice. That was a good point to, like, I've learned something about the networks. I've learned that actually, if I don't use gradient clipping, I might get away with it, but things that, this is an unstable problem, and large gradients are a problem. I need to deal with those. So then I thought, well, okay, let's chuck a bit more data in, and see how that goes. And this was even more upsetting because I was like, this definitely worked, and actually this doesn't always do this. It turns out that it will either do this or it won't do this, and it depends on which samples you choose. You shuffle your data, like it's sampled from the training data, but I'll sample a random subset of my training data, and some subsets are fine and some of them are not. And this is quite like, it just doesn't like some of my data points. Like, are they, I don't know, have I got none in my data? Like, my data's all good. I've gone through, I've looked at it. The numbers are all fine. It turns out that what happened, a bit more kind of digging and investigating in this kind of still fairly small problem, and I found that actually sometimes you get, by chance, you've missed a duplicate. And so you have two images that are in fact effectively right on top of each other. And so what you can go and do is just say, well, I want things to be about 0.2 away from each other. If they're more than 0.001, then, well, either they're a true pair and they're so close together they're never going to separate, or they're a false pair and that is a bug in my data. That is a problem with my data and it needs cleaning out. So you can just strip these out. And I did this, and that was great. The world was happy again. And I got nice loss numbers. I'm afraid I haven't got a nice GIF for you for this one. But one of the other things I found was I was still kind of not doing exactly what the papers talk about. Like, I'm yet to find a paper that actually says you should do metric learning and not use L2 normalization. So what this specifically means is normally, if you, like, let's say you're using a 3D space to consider everything. So you have this nice big kind of 3D representation of all of your images, and the simple thing is you just project them to somewhere in the space, and you just measure how far apart they are. And all this says is you want to constrain them to be on the surface of a sphere. So you don't want to be anywhere in the space. They have to be somewhere on the unit sphere in this space. And then you measure the distances between them just the same. And this is commonly referred to as commonly kind of cited as a thing to do, and it's what all three of these papers, and many others as well, which I haven't cited here, talk about doing. But I haven't found actually any good justification about why you have to do this, but I thought, well, that's quite interesting. So I went back to my network, and I chucked in the L2 normalization. It's fairly simple. It's just a step you do in the middle, and you can still backpropagate through this, so it's fine. And it sort of does something weird. It kind of means that all the losses are smaller, but they hardly move. And I spent quite a while playing with this, but I actually came to the conclusion that while there's several papers that say this is great and it sounds fantastic, and hey, I should follow the literature, I actually concluded that if I don't normalize this, it works great for me. So that's what I'm going to do. And I concluded that while reading academic literature to understand the problems is fantastic, if there's no real justification in the literature as to why this is great, it's just a choice somebody's made, then you know what, it works. It works. And so this is a thing to come back to for me, but I concluded that I'm quite happy to just take a model that does work and use it, even if it isn't like what's cited most commonly. So the specifics of what I ended up using, or where I am now, I should say. This is still very much work in progress. So this is the network that I started with. So this is effectively the early layers of ZFnet, and then all the subsequent layers are fully connected, and so I simply ignored those, threw those away. And so all of our images are passed through this to this point. We just literally do mean subtraction, but we don't do any other whitening of our data. And so the output of this is a 6 by 6 by 256 kernels kind of representation, and I pre-calculate that for all of our images, and then I can just use, there's just vectors that I can use to kind of build the network on. So the network I build on top is fully connected. I use ReLU. I use the contrastive loss. It's working quite well, and a little bit more playing, and I found that actually putting in 2 layers is very nice. It gives you more nonlinearity, a little bit more descriptive power. And I find actually standard setup for stochastic gradient, for momentum stochastic gradient descent works really well. So I assume everyone knows stochastic gradient descent. Momentum is very similar, but it just has a term that basically takes the last gradient update and combines that with the current step, which helps to stabilize things a little. Gradient clipping was great, and I found a little bit of weight decay again, just helped a little bit. My next slide, I was hoping would be more impressive, but the model still kind of in the middle of training. So this is after about, I don't know, about 20 hours of training on a pretty large number of our images. And it's quite a mess. But what's quite reassuring to me is that we are starting to get the different poses are actually converging. So these are all the same shoe. And they are coming together in the same bit of the state space. And we're getting these kind of things. They're all moving together. So there is definitely some motion in the right direction. But this is, I think, probably a good month of me playing around with this kind of network before I'm going to get something that's going to be like ready to use. But I did try and make a few predictions with this to see how it works. And so I picked a random collection of images, a random few predictions, and some come up really, really nicely. So about half of them, actually, if you set kind of quite a tight threshold, about half of them come up really nicely. And so you get like different images, and like these are different colors, I should say. I can see on my laptop. They are definitely different colors. So you get quite similar, and these actually have a slightly different pattern, but they come up as being duplicates. But the downside to this is I'm still finding it's picking up kind of collections of things that, I mean, these just aren't the same, right? I should say, sorry, the top and the bottom are the ones that are supposed to be the same. They're just not the same. So this is all work in progress, right? This is still definitely getting there. But I think the takeaways for me, like the things that I definitely concluded from having gone through this process is that there's kind of a few things. Neural networks are, they're known to be able to describe arbitrarily complex functions. And this is true. You can do amazing things with them. But the problem is they will exploit any issues with your data. They will exploit any errors, any artifacts. They will work around and learn in new ways that you didn't think of that might not actually be useful to you. So it's like trying to teach a really intelligent child that doesn't really want to do what you want. It's going to do whatever it feels like. So more data can be very effective. And for those of you who are in this talk, we throw lots of data at classification problems, and the more data you put in, the better your results are. This does work really well. But when you're trying to get your model working, it's tempting to think that the problem is that you haven't put enough data in, and that's where it's going wrong. And what that means is that every time you make a decision, you then spend 6 hours waiting for the results to come out, only to go, oh, it's still broken. And then you can lose a lot of time just continuously thinking that, oh, it's just, if only I had a bit more data, it would generalize. It seems like an easy kind of pitfall to have when it's known that lots of data is good. But I think simplifying cases where you just have 1 or 2 points, when things where you can really understand what's going on, and when it doesn't work, you can follow the maths, is really, really useful. Neural networks can be difficult to interpret. I mean, we've seen, there's lots of ways of visualizing neural networks. There's lots of ways of looking at the activations of layers, and you can look for which parts of the images are receiving attention from images, and there's lots of things you can do. There's more and more increasing ways of visualizing networks coming out. But they're still known to be very black box. They're still hard to know what they're going to do, what behaviors they'll have in any given case. So they are a very tricky model to use. But I think people use this as an excuse to then just kind of not do this, just to simply assume that it's OK to not understand the network and then to kind of focus on other aspects of the problem. But I think if you're going to use something that's more complex and more difficult to understand, then you need to work harder to understand what it's actually doing. You need to simplify the problem, make sure you understand what it is, and then build up more slowly. Otherwise, you can just, as I did, get yourself into some very tricky scenarios where you just have too many moving parts and you don't know which piece is wrong. But most of all, it was very good fun. It was really entertaining doing this. I've learned quite a lot about other machine learning algorithms, and this to me was an entirely new kind of area to research. So I would say if anybody is interested in playing with this stuff, it is fantastic fun. So please don't let me discourage you. Yeah, thank you.
Very nice talk, thank you.
Thanks.
You didn't really talk anything, or didn't talk about regularization at all. Can you say a few words on that, whether you found it useful or how you used it?
Yeah, I can. I didn't do that much work on the regularization. I didn't do much on regularization here because, for me, a lot of the problems I had in getting this working came down to understanding that the network can describe what you're doing. But I think you're right. Regularization is extremely important. Increasing the size of the image data set certainly can help, and being able to get to the point where regularization is effective, effectively solves that kind of train test problem is really useful. And so all the time I've been doing any of these things, I always run train and test at the same time. And for the small data sets, you very quickly do hit that point where they diverge very, very horribly. I've played around with things like dropout. This uses actually, the network I'm relying on underneath has batch normalization, which is a very effective form of regularization. And it means that my input representation is already extremely stable to a lot of variations in the images. So it wasn't as sensitive in this case. But I think where this is likely to go is we want to take the multitask problem that we've done for classification, gender, and color, and I want to retrain this. I want to add this as a task. So we pass the images through, and then we pass 2 different images through, or pass triplets through, and then we do all the different classifications, and we do the metric learning. And that should hopefully mean that we can find out this is address, and this is also address, and are they the same or not? And that kind of thing I think would be good. And I know we've spoken about the nature of multi-task regularization, so I think it's definitely a good way to go.
Hi.
Hi.
Your algorithm was about classifying duplicate images, but your problem is duplicate products.
Yes.
Have you got to the stage where you are saying these 2 products have like a certain number of duplicate images in common, or how are you going to deal with that?
So the reason for approaching the problem on an image basis is if you clean your data set up and you're left with you're left in the position where that yes, you have a set of images that are all from the same product, you don't have any labels left. It's kind of hard to separate the set of images and do something with that. So the idea is to take the simplest unit that you can work with, which is we know these are all pictures of the same product, so let's see whether you can take any 2 images from a product and determine they are from that same product. Once we have a stable space for working in, we want to then look at using independent ensembles of those images to say that given a collection of images from one, you can identify it's an image. And actually have the network do the averaging on that basis. But there'll probably be a step in the middle where we do try the kind of collaborative approach where we say,
makes sense.
That. So, that's a good point.
So before neural networks came along, people approached very similar problems using shape descriptors in pattern recognition.
Yeah.
And in fact, there is quite a rich body of research, starting with image moments and all kinds of sophistication on and forward about shape descriptors. So I wonder if you'd add some shape descriptors to the images, maybe the neural network would be given the right hint it needs to learn the right features.
Yeah, I think that's a really good point. We actually have an existing product duplicate candidate suggestion like service in production that relies on BRISC features, which are kind of like SIFT features. They're very similar. So we use this and it works in certain cases, and there are certain classes of images that are really good. It produces really good candidates for, but there's lots of classes that it's very, very bad at. So yes, I think that's a really good idea, and I think we could definitely concatenate our deep representation with the BRISC representations and use that combined thing to learn the duplicate section. Yeah, definitely.
Concerning the different perspectives of the same object, in principle, it's not very different from algorithm reconstructing panoramas from pictures. Do you think there can be some collaborations of this kind of algorithms and then classification by neural network?
I missed the start of that. Could you?
So in principle, reconstructing, understanding that several pictures of a show from different angles is a single object, is not too different from building panoramas from pictures. And then obviously understanding whether it works or not.
Yes. Yeah, that's a good point. Some of the other papers, which I haven't cited here, talk around trying to map. So usually the research around this is around face detection, and they talk around trying to map faces onto a 3D object and use that. But those papers were the results of those papers have been substantially beaten by just training networks given a variety of different images and just minimizing the ability to distinguish they are the same. So there have been approaches around that, and I think that's what's stimulated a lot of the research into this. But the triplet loss and the contrastive loss are both have had results that have beaten more complex, more kind of spatial approaches at the moment. And training in this way is quite easy to set up. I think I need about 25 lines of code to do the contrastive loss training without before you need any cross-validation, all those things. Whereas I think the more of that kind of problem is, I think, harder to pose. So I think it's an interesting area of research, and it may yet be that is the more kind of successful, but it's harder, I think, to approach from the outset.
Any other questions?
Thank you.